daily digest of events. You should have received an exit survey for the conference. So if you're able to fill that out, it should be pretty quick. We would really appreciate it. I also put the link to the survey in the Discord. So any comments you have about the conference really is useful going forward. So please fill that out if you can. The next thing I wanted to say is we're very pleased to have Ty here for our last plenary talk of the conference. So before I do the official introduction, I wanted to say how we'll take questions. So Ty is very happy to be interrupted by questions in any way. So you can either unmute and ask questions, or if you're feeling kind of shy or have some technical difficulty, feel free to put the questions in the chat, and myself or one of the other organizers will read it out. Okay, so with that being said, we are delighted to have Ty Ghaswala here as our final plenary speaker for NCNGT. Ty received his PhD in 2017 from the University of Waterloo, where he was advised by David McKinnon and Doug Park. He was then a PIMS postdoctoral fellow at the University of Manitoba and a Serge postdoctoral fellow at the Université de Québec à Montréal. I hope no one here knows a lot of French. I hope that was okay. Or I mean, I hope you know French. Sorry that I don't know French. Okay. He is now at the University of Waterloo with joint appointments at the Center for Education and Computing, as well as the Pure Mathematics Department. So I'm thrilled to let Ty take it away to tell us about small covers of big surfaces.
Right. Thanks very much for the introduction and the invite. I'm very happy to be here. This was my favorite conference that I went to during the pandemic by a long way. So I'm really honored to be invited to give a plenary. As City mentioned, please interrupt. I don't want it to feel like the beginning of the pandemic where everyone was just talking to blank screens. If you want to unmute yourself while you laugh at my jokes, whatever you want, it's fine. Go for it. So today, what I talked to you about today is going to be joint with Alan McClay. He's at the University of Strathclyde in Glasgow. There he is. And the goal is, I want to sort of maybe convince you that infinite type surfaces are interesting and important to look at. And there are lots of sort of basic questions that we don't know the answers to at this point. And failing that, I just want you to be convinced that it's enjoyable to work in these areas and think about the problems that come with them, because it's really fun mathematics. And on that, let's go. So here's what we're going to do today. We're going to talk about a reconstruction theorem for finite sheeted covers of infinite type surfaces. Okay, so I'll tell you what I mean by these things, but that's what's going to happen now for the next 50 minutes or so. So what do I mean by a reconstruction theorem? These are among my favorite theorems in mathematics. All right, so here's one super old theorem, Darboux from the 1800s. It's kind of lost. If you take a set bijection from R2 to R2, just a Euclidean plane, and it preserves lines, so you take any straight line, all the points on that line get sent to points on the same line. Okay. So there might be permuted, it's not continuous or anything. It's just a set bijection that preserves lines, sends lines to lines. Then you can actually reconstruct that F is actually an affine map. Okay, so first the way you do this is you start with this information that lines get preserved, and then you argue that, well, intersections have to be preserved, and then you argue that quadrilaterals have to, parallelograms have to be preserved. And then once you're there, you can sort of make a few more leaps and get that F is affine, right? And the point here, why do I call this a reconstruction theorem, is because if you have an affine map, then for sure lines get preserved. Right? Then you're asking, what is the minimum amount of information I need to reconstruct the affineness? Right? So it's like the hard direction of an if and only if, more or less. So this is a really cool theorem. It's fun to try to prove it for some definition of fun. Now, here's a more modern reconstruction theorem, also a fantastic, beautiful theorem. It's more-star rigidity. So if you have complete finite volume hyperbolic manifolds, and as long as the dimension is big enough, then you take an isomorphism, a group isomorphism with their fundamental groups. You can reconstruct an isometry that induces that isomorphism. And again, the isometry always gives you an isomorphism. But now it turns out all you need to know is that there's an isomorphism of a fundamental group to reconstruct the isometry of the hyperbolic manifolds. Great. So these are what I mean by a reconstruction theorem. You're taking like shadows of information and reconstructing what came out of it. Let's talk about surfaces. So for us, surfaces are second countable. So no long line shenanigans or anything like that. Just your usual surfaces. Everything's going to be orientable and everything is boundaryless unless I say otherwise. You have finite type surfaces and infinite type surfaces. Finite type surfaces are those where the fundamental group is finitely generated, or intuitively, there's a finite amount of topology. Now, here's an example on the left of a finite type surface, and it's infinite type otherwise. So the right-hand side there, you imagine that the genus keeps going off all the way that way. It's more effective virtual talks because your hand actually leaves the screen and then you don't know how long my arm is. It just keeps going. It's good. Okay. So here's a nice theorem, and this is probably the theorem that made me go into mathematics. I was exposed to this, lucky enough to see this at a high school camp at the end of grade 12, and it's just the most beautiful theorem ever. It's a classification of surfaces theorem, right? And it says that if you have, for finite type surfaces, the homeomorphism type of a surface is determined by two numbers, right? Remember, I don't have boundary, right? So two numbers, and it's this genus and the number of ends. So I'll talk to you about ends in a sec, but for now, you just think of it as like a puncture or a part where you can just keep going off without hitting the end. Okay, so here's an example. Here's a genus 1 surface with 2 closed disks removed. That's a genus 1 surface. The number of ends is 2, and there's 2 sort of punctures here. They're big punctures, but they're punctures. Throughout the talk, blue crosses or blue dots are going to be deleted points on my surface. So here I've got a genus 0 surface with 3 punctures. It's a sphere, and I've cut 3 holes out of it. Or here I've got a genus 3 surface with 0 punctures. This is amazingly powerful, right? We can say things like, when you have a classification theorem like this, you can say things like, you know, I have a degree 3 cover of a genus 2 surface, so I know it's a genus 4 surface. Right? The fact that I can just say this is kind of remarkable, because if you're just learning some topology and someone tells you that, you're like, this sounds outrageous to be able to say something like that. Even better, you give me any 2 non-negative integers, there is a surface. Right? So it's a full story. It's just magnificent. It's so powerful that you forget that you use it when you do use it. This is how good it is. So what about infinite type surfaces? Well, here are some. Here's one called the Loch Ness Monster. It's a shockingly bad name, but here we are. Stuck with it now. If you draw the right picture, it kind of looks like the Loch Ness Monster. At least what I think the Loch Ness Monster looks like. Here's the ladder. So this is sort of, you've got an infinite cylinder going off in both directions, and then you got genus all the way along. All right. This keeps going. Or you could take a plane and you could delete every integer coordinate. That's a perfectly good 2 manifold. It's orientable. It's got lots of topology. Or you could take this surface, which is a cylinder, along where my mouse is going, and then I sort of glued in a cusp at every integer point along a cylinder, let's say. This is called a flute surface, a better name. Okay, it kind of looks like a flute if you squint. You could take a sphere and then delete a Cantor set if you want, and you are left with a perfectly good manifold. That's what the Cantor set's going to look like for this talk. Just a couple of lines. Or you could take an infinite trivalent tree that's based somewhere. Okay, infinite trivalent tree, and thicken it up and look at the boundary of that. And that's what I've got in front of you there. This is called a Cantor tree. So the branching just keeps happening. Or if you're a sociopath, you could take the tree and then just like stick a genus in at every vertex of your original tree. That's called the blooming Cantor tree. There's lots of very creative names here. Or you could do this. You could take 2 planes and you could glue in a pillar at every integer coordinate. This is, again, a perfectly good 2 manifold. And look at the sort of boundary of this. This is like an infinite Parthenon. I could take a 3-ended surface where every end is accumulated, has genus going off as far as you can go. It's like a ladder, but with 3 prongs. And then on one of the prongs, I could just puncture it all the way out. Now, it's like, well, what can't you do, right? You just have full freedom, basically. So here are the pictures I drew before. Which of these are homeomorphic? This is the question we're going to try and answer right now. Right. Okay, so in order to talk about the classification, so there is, spoiler alert, there is a classification, which is just like unreasonable to expect, but there is a classification of infinite type surfaces. We have to talk about the ends. So an end of a surface, intuitively, is a way to go out to infinity. Right? This is the way you want to think of it. So here are some ways to go out to infinity. What I've drawn here are images of the half open interval, so from 0 to infinity of the real line. Okay. And what we're going to do is we're going to take the set of all of these things with some adjectives attached to them and put some equivalence relation on them to define what an end is. Now, what we would want is that all the things to the right, any arc that goes out, any ray that goes out to the right is going to define the same end. Any ray that goes out to the left is going to define the same end. And if rays go out to the same puncture, we want them to define the same end. So ideally here, you've got an end for each puncture, a big end out the left and a big end out the right. So we're going to put an equivalence relation on proper maps from 0 to infinity into your surface. Okay, now what's proper here? That is not a proper map. Right? Proper means the pre-image of any compact set is compact. Properness turns out to be the right sort of category of map you want to think about when you're talking about non-compact things in general. Properness is really important here. So that's not proper. We don't want any of that nonsense happening. So what's the equivalence relation going to be? So whatever it is, I want these two yellow ones to be equivalent. And I don't want the yellow ones to be equivalent to the red or to the magenta or the blue. Okay. So let's just start throwing potential adjectives here, right? So if it's homotopy, if you just say two ends or two arcs are, rays are homotopic, that's too weak. Because what you can do is you can take one of the yellow rays, you can shrink it down via a homotopy to a non-proper embedding, turn it around and shoot it off the other side. So this is too weak. You'll have the blue ones being homotopic to the yellow ones. We don't want that. So maybe you want to add proper homotopy in, which means your homotopy itself is a proper map. That turns out to be too strong. You can show that eta and gamma are not properly homotopic. So somehow you want something in between. And the in-between thing is this weird ladder homotopy kind of thing, right? Where it's a homotopy, except it's only a homotopy at the natural numbers, right? So there's some arc joining gamma of 0 to eta of 0, gamma of 1 to eta of 1, gamma of 2 to eta of 2, etc., etc. And you want it to be proper, right? So it's like a homotopy, except it's sort of some kind of like little skeleton of it. And you want it to be proper. Now, the properness is because I can find a homotopy between the yellow one and the blue one that, like I'm describing, except then you'll have infinitely many arcs and infinitely many rungs of your ladder, let's say, that intersect a curve over here where my hand is, where my mouse hand is. And then the pre-image of those infinitely many points on your ladder is going to be non-compact. So that's not proper. We don't want that. Yeah, so this turns out to be the right definition. And it's equivalent to, if you've seen an inverse limit definition of complements of compacts, you can check that it's equivalent. But I like this because it really, we always like to say that an end is a way off to infinity, and I'm showing you the ways to infinity, right? It's these infinite arcs, or these rays. One-ended rays is what we've called them. Cool. All right. Any questions?
Okay. So is this the definition? You say it's the same as like the inverse limit definition. Is that like homotopy on compact sets?
So the inverse limit definition is you take an inverse limit of complementary components of compact sets. So you take a compact and then you sort of take bigger and bigger compacts and you look at the complementary components. And each sort of chain of complementary components gives you an end.
Okay.
It's the same as this, yeah.
Thank you.
No worries. Great. Okay, we're going to call the set of ends of sigma. So it's these one-ended rays with this equivalence. We have to topologize this set, right? And here's what you do. You take a compact set and you look at a complementary component of it. So here's a perfectly good compact set. This curve K. K for compact, and then the complementary component. And you look at all the, so the basic open sets of your topology are going to be all the rays, all the ends defined by rays that are contained in the same complementary component of a compact set. So all the rays that shoot off in this complementary component are going to form an open set. They're going to form a basic open. All the rays that shoot off on this side are going to form a basic open. And then you could draw another curve over here and then look at the ends that are complementary to that, etc., etc. Okay. This is hard to digest, but let's see an example of how this works. So we need one more piece of information before we look at the space of ends as a topological space. And there are two different types of ends that we have to consider. You either, as you're going off in a direction towards an end, you either see genus all the way out or you don't. Right? So these two big ends, these red ones, as you keep going, you just keep seeing genus. Right? The blue ones, you don't. At some point, you can pass some compact set, and then outside there, there's no more genus. All right, so all these punctures are planar ends. They're called planar ends. The ones that are accumulated by genus are called accumulated by genus. So what does our topological space look like? So we now have a topological pair. You have your end space, and you want to pay attention to which ends are accumulated by genus. So here's what this one looks like. If I walk out the left, I have a bunch of planar isolated ends that accumulate to this big end on the left. And that's exactly what's going on here. Okay, so this is just what the end space looks like as a topological space. If I go up here, there's one end accumulated by genus, but it's also accumulated by isolated planar ends. So that's what's going on here. And on the right, I've only got one end there. And it's isolated because, well, I could take a curve, say where my mouse is, and then there's only one end in the complementary component to the right of that. So it's isolated. And there it is. There's an open set containing just that thing, so it's an isolated point. So this is what the end space looks like for this surface. Okay, questions about this? Okay. So here are some fun facts about the end space. The end space is always homeomorphic to a closed subset of the Cantor set. All right, and the way you show this, so that there's this universal property of closed subsets to the Cantor set. If you have a topological space that's totally disconnected, compact, and metrizable, it's a closed subset of the Cantor set. If you add in the adjective perfect, it becomes the Cantor set, homeomorphic to it. Okay, so you can show that these adjectives are satisfied for the end space, and you know that the end space is homeomorphic to a closed subset. And even better, the ends accumulated by genus is a closed subset of that. So associated to a surface, you have a closed subset of the Cantor set and a closed subset of that. And here's the classification of surfaces, which was first proved-ish by Caracciato and then cleaned up in the stronger version, the version I'm about to state, was proved by Richards 40 years later in his thesis. So a surface, infinite type, this is true for finite type as well, but it's determined by two pieces of information: the genus, which could be infinite, only countably infinite, because the surface is second countable, you can't have anything worse, and the homeomorphism type of the topological pair, the end space and the ends accumulated by genus. Okay, so this is a topological pair. And what it tells you, so this surface here is infinite genus and one end. This surface here is infinite genus and one end. They are homeomorphic, even though they have no right to be. Yeah. These two surfaces are not homeomorphic. This one has two ends. This one only has one. Right? To me, how do you identify how many ends, or like how do you separate ends? It's like if you can separate the two ends by a compact set, they're going to be different. Over here, you can't really find a compact set that sort of gets rid of two directions at infinity, but over here you can. You just draw a separating curve. This surface, genus 0, the n space looks like a bunch of isolated points accumulating to one point for both of these surfaces. So they're homeomorphic. Or if you want, the n space looks like the set 1 on n in the real line, union 0, as n for positive integers n. These two sets have a Cantor set of n's. These two surfaces have a Cantor set of n's. Right. You can think of the n space over here as strings of zeros and ones, whether you go left or right at each vertex. So sure enough, you're going to get a Cantor set over here. And over here, I remove the Cantor set, and if there's any justice in the world, the n space is going to be a Cantor set. And it turns out it is. So here's the strong part. Not only do you have a classification up to homeomorphism, but any possible data exists. You give me a closed subset of the Cantor set and a closed subset of that. There is a surface with that n space. Right? There's a minor caveat I have to be careful of here. If your genus is finite, you can't have any n's accumulated by genus. But other than that, anything goes. Full classification. It's just amazing. No right to exist, but it does. We should exploit it. And when you have a classification theorem, it's usually very powerful. Great. Any questions about the statement of the theorem?
Yeah, I mean, this is already very beautiful, but I'm sort of wondering, what about the diffeomorphism type? I mean, is there something like a Kirby-Torus trick in this infinite type surface business?
So for two manifolds in general, if you have two manifolds that are homeomorphic, they are diffeomorphic, even for this non-compact setting.
Thanks.
I mean, sorry, I hesitated because I just wanted to make sure I wasn't saying something false because now I'm recorded, you know. Anyway, I think I'm pretty sure that's true. Yeah. Okay. So a good question to ask at all points in life is like, why? Who cares? So first thing is that if you meet a surface in nature, you should expect it to be infinite type, right? Being finitely generated as a group is like 0% of the groups. You should expect a surface to be infinite type. Also, there's uncountably many of these and there's uncountably many finite type surfaces up to homeomorphism anyway. You know, there's a classification. As far as I'm concerned, as soon as I have a classification, I want to think about it really hard and see what I can get out of it. And there's lots of research right now. It's a very active area into mapping class groups of these surfaces, which initially I was a little concerned it was just going to look like a copy and paste of the finite type world, but really now it's taken on a life of its own. These are really interesting groups. They're what are called Polish groups. They're not locally compact, but you can still get your hands on them. And there's all sorts of really beautiful stuff going on, which I'm not going to be able to talk about today, unfortunately. But even with the sort of powerful mapping class group stuff that's happening, there's lots of questions about the surfaces themselves that we still don't understand. So let's talk about that. Let's talk about covers. Pop quiz. I have a surface. It's that surface. It has genus 2 and 3 boundary components. And so here I have boundary components. The Euler characteristic is -5. You can check this. And now let's say I had a 3-sheeted cover of this surface. There are a couple of things I can say here. The Euler characteristic, what's the Euler characteristic going to be? It has to be -15. The number of boundary components is less clear, but you know, above each boundary component, you can have between 1 and 3 components mapping to it. Either when you restrict to the pre-image, you're like a connected cover or you're a disconnected cover, and then you work out what's going on there. So each pre-image of a boundary component has between 1 and 3 pre-images. So the surface upstairs has between 3 and 9 boundary components, inclusive. Here's a relatively unknown theorem of Massey from 1970, cited a whole number, all of 2 times according to MathSciNet. And it says that, you know, as long as these 2 conditions are satisfied, there is a cover. Right? So, you know, you have 2 surfaces, you look at their boundary components. As long as the Euler characteristic multiplies, and your number of boundary components upstairs lies between these two bounds, there's a cover between those two surfaces. That's great. The paper's really nice. It's like 6 pages of pictures and 4 pages of text. It's great. It's really good mathematics. It's a nice, full answer to this question. This is a reconstruction theorem in some sense. Where you know that if you have a cover, you have this information, but where can you reconstruct the cover just from that? So let's ask the basic question about covers of infinite type surfaces. I'm going to restrict to finite sheeted covers, and I'll tell you why in a moment. So when does there exist a finite sheeted cover between two infinite type surfaces? Let's do some examples. Here's a 3-sheeted cover of this 3-ended infinite genus surface over this 1-ended infinite genus surface. So I take my 3 prongs, I put a genus in the middle, and then I'm going to rotate around that genus. And because I'm rotating around a point that's around an axis that doesn't intersect my surface, this is a free action. You quotient by it, you get a covering space. You get a regular covering space, in fact. There you go, 3-sheeted cover. All right, this one. So here it's my artistic qualities aren't really shining through here, but I'm taking an infinite cylinder, gluing handles on the top and bottom all the way down in either direction, except in the middle where I'm gluing in a ladder up and down. That's what the surface on the top is. And now I'm taking an axis through that initial cylinder, not intersecting the surface anywhere, and rotating by pi. Again, this is a free action. I quotient down, and you can maybe convince yourself that what you get is a 3-ended infinite genus surface downstairs. So here I have a 4-ended surface covering a 3-ended surface, whatever. It exists. It's there. Things can get kind of interesting. Now, here's the sad thing when you start doing this stuff, is that you want to throw, at least I want to throw, usual algebraic topology invariance at these things. Fundamental group, right? Look at, somehow that'll help us out. Or homotopy, homology invariance, homotopy invariance, whatever. Any homotopy invariance, right? Let's throw something at it to start classifying covers. You can't. And the reason is because every infinite type surface, well, the fundamental group is the infinitely generated free group, countably infinitely generated free group. And they all have contractible universal cover. They're all hyperbolic. They all have H2. And this means they're all k-pi1s. So all the infinite type surfaces are homotopy equivalent to each other. So you're not distinguishing them by any homotopy invariance. They're all homotopy equivalent to each other because they're all k-pi1s. You know, which is just like, well, what do you have? You have nothing left, right? Almost. You still have the n spaces. Okay. So I know this is unsettling the first time you hear it, right? That like they're all homotopy equivalent. Like, why are we here? So if you have a finite sheeted cover, the covering map itself is a proper map. And when you have a proper map, you immediately get a continuous map from the n spaces, between the n spaces. And this is a general topological fact. Here are some disappointing observations though. So I want to study this map to try and get some leverage here. Well, the induced map doesn't seem to respect, well, it doesn't respect whether or not your end is accumulated by genus. And nice theorems are of the form, well, if P is a covering map, then P bar is a covering map. But that's not true either. And these are things you'd want to be true because it would be beautiful if they were, but they're just not. So here's an example which breaks both of them. Okay, so what I've got upstairs is a ladder, and then I've skewered it right through those blue punctures. All right, so I've skewered it right through those blue punctures. If you've seen a hyperelliptic involution before, this is exactly that. Okay, so I'm skewering it through these blue punctures. And then just for good measure, I'm going to put punctures at the top and bottom as well. Right? And since I'm skewering through the punctures, when I do a rotation by pi, this is a free involution. It's a free finite group action, so I get a covering space. And what happens downstairs, what you're left with, when you do that, is a genus 0 surface with a whole bunch of ends. These pink ends get mapped 2 to 1 down, and the blue ends get mapped in a 1 to 1 fashion down. So not only does the end accumulated by genus here get mapped to an end not accumulated by genus, but it's 2-to-1 sometimes and it's 1-to-1 sometimes. It's not even a covering map. Forget everything, right? So these two things aren't true. That's okay. Here are some encouraging things that you can say. So this is something we proved. Take a finite sheeted map, finite sheeted covering space. Now, this is something you could put on an exercise in a like third-year course. All right, once you have a bit of points-set topology under your belt, it's nothing. I mean, it's a great theorem, of course, but there's nothing terribly difficult about it. You have to unwrap some definitions, and it all falls out. So if you have a finite sheeted cover, here's what you can say about the induced map on the end spaces. It's continuous. That comes for free from properness of the map. It's open. It's surjective, and the pre-image of any point is at most the number of sheets you have. Okay, so you have all these nice little adjectives. It's continuous, open, surjective, which is kind of like a quotient map. And then you know the pre-image of any point, the size of the pre-image of any point. Great. So, I mean, you could ask, is this enough? And when we first proved this forward direction, I thought for sure there's no way this is enough. And then over the next week or so, or 2 weeks, Alan sort of started putting up some notes in our shared overleaf file, and he started making some definitions which implied that he was trying to prove that it was enough. And I was like, this is ridiculous. He's an unreasonably optimistic man, but it turns out that it is enough. So here's a reconstruction theorem for covering spaces, and this is a Massey theorem. Right, sort of the bare minimum information you need to reconstruct a cover. So suppose you have closed subsets of a Cantor set and a continuous open surjective map where the number of pre-images of every point is bounded uniformly. Right, so it has a hope of coming from a cover. But this is just a function between closed subsets of a Cantor set. Then you can construct a cover that induces that function. This is the theorem. Right, so then you can find surfaces which have n spaces homeomorphic to S and T and a covering map, which induces the function. And that's what I mean. This square commuting is what I mean by inducing the function. You have a homeomorphism between the n space and S and T, and then, this square commutes. So yeah, this is, in my mind, this is Massey's theorem for infinite type surfaces. So I want to, I'm usually wary about proving things, but I want to give you an idea of the proof because there's lots of interesting little tricks for covering spaces here. Let's do a very baby example. I'm going to start with a function from two closed subsets of the Cantor set, between two closed subsets of the Cantor set. Here is a closed subset of the Cantor set. It has 3 points in it, 3 discrete points. Here is a closed subset of the Cantor set. It has 2 discrete points. And my function sends the pink ones to the pink one and the green one to the green one. That's my function. And now what I want to do is I want to reconstruct a cover that gives me that map on the n spaces. Here's how we do it. Okay, so I'm going to start by building my surface downstairs. So my surface downstairs has 2 ends, and I'm going to create it by taking genus 1 surfaces with some number of boundary components. Here I only need 2 in each case, and gluing them together and creating some kind of compact exhaustion. Okay, so I'm just gluing together a whole bunch of genus 1 surfaces, and my pink end goes to the right, my green end goes to the left. Now I have to construct the covering, the covering surface and the covering map. So I'm going to start in the middle, and first thing I'm going to do, I've already numbered them. Okay, so I have to number my points upstairs in such a way that the sum over every pre-image of a point is constant. So here I've just numbered, I've given these points labels so that the sum of this is 3 and the sum of the pre-images of the green is 3 as well. Okay, so I'm going to create a 3-sheeted cover. That's what I'm doing. So part of the hard part of this theorem is showing that you can actually find a numbering in general. Okay. But once you have that, here's the construction. So I have a 3-sheeted cover. I start in the middle here. I'm going to take a 3-sheeted cover of this genus 1 surface. By a genus 1 surface, with 3 times the number of boundary components. So there's this magic thing that happens with Euler characteristic that tells you this can always happen. If you have a genus 1 surface downstairs with some number of boundary components and a K-sheeted cover, you can make that covering surface a genus 1 surface with K times the number of boundary components. I guess Massey's theorem tells you that one exists. And I'm going to keep track of which boundary components map where. And here's a really nice coincidence, is that because I'm choosing this to be a genus 1 surface, if I restrict my covering map to any of these boundary components, they're 1-to-1. They're no longer 2-to-1 or 3-to-1 or anything. They're homeomorphisms onto the boundary components. There's no twisting that happens. This is going to be really important for gluing everything together. Okay, so I start in the middle. I have a 3-sheeted cover in the middle, and I want to build outwards. So I'm going to allocate 2 of my pre-images of this to the end upstairs with a 2 on it. Right, so these 2 are now allocated in my mind to this end up here. And this 1 boundary component is allocated in my mind to this end over here. And these 3 are allocated to this 3 over here. And now I play the game again. Above this piece of my surface, I'm going to take a 1-to-1 cover because this end is labeled by 1, and a 2-to-1 cover, a disconnected cover now. And then glue them on. And over here, I want to take a 3-to-1 cover because this is allocated to a number 3 and put that over the top. So there is a 2-to-1 cover, which is a genus 1 with 4 boundary components over this surface. And there is a 1-to-1 cover, a homeomorphism. There is a 3-to-1 cover here. And then you just keep playing. And the reason you can stitch these covers together to make one big cover is that the degree of the map from this boundary component down, from the left and the right, they agree because they're all just 1-to-1. Once you have that, you prove a little lemma that says as long as your degrees agree on the boundary components, you can glue all these things together to build a big covering space. And then you just build it outwards and so on. And here I've got a perfectly good covering of a 2-ended surface by a 3-ended surface in such a way that this end, these 2 ends on the right, these 2 pink ends map to the pink end, and this green end maps to the green end. So this is the theorem for one surface, and then you do it uncountably many more times, and you have the theorem. But that's the idea. You sort of stitch the covers together. Cool. Any questions about that?
Is there any chance of doing it with Galois covers?
Oh, that's a great question. I don't know. I think you'd have a hard time. Yeah, I think you'd have a hard time. There's probably hope. There's always hope. It's just not very much hope, I think. Yeah. Okay. So here are some applications of the reconstruction theorem. So Tarek Agab, Prem Patel, and Nick Vlamis, a couple of years before us, proved this statement, but using completely different techniques. Do the same thing. So I want you to notice that my construction before, it does require every end to be accumulated by genus, right? So the theorem is just about maps between closed subsets of the Cantor set, and then I get to choose which ones have genus. And I need everything to have genus. So it's not as strong as you would like, maybe, but it's as good as we got so far. But what you can conclude is that if you have an infinite type surface without planar ends, so every end is accumulated by genus, there is a cover of it by itself, of whatever degree you like. Because you apply the reconstruction theorem by just taking the identity map and then number everything upstairs with K, and then just run the machinery. Cool. We can also think about commensurability classes of infinite type surfaces. So commensurability classes are, it's a way of organizing yourself in some sense, of grouping surfaces together that are not homeomorphic, but pretty similar to being homeomorphic. So here's what it means to be commensurable, is that if you share a common finite sheeted cover, you're commensurable. 2 surfaces are commensurable. And it turns out to be an equivalence relation. It's not obvious by the definition, but it's true. So here the commensurability class for finite type. Well, let's say compact, so you have boundary. There are exactly 6 commensurability classes. And they are the hyperbolic ones, the Euclidean ones, and the spherical ones, with or without boundary. This is kind of nice, right? This idea of commensurability is doing the geometry for you. It's splitting it up. It's telling you what things should be grouped together. So wouldn't it be nice if we had some kind of organizational tool? Because even though we have a classification of surfaces, there's a lot of them. It's uncountably many. It's hard to sort of prove theorems in general. So maybe you can prove theorems for certain commensurability classes. So here are some useful propositions to sort of get at the commensurability classes. So first is the forward direction of the reconstruction theorem. If you have a finite sheeted cover, then you have all these nice properties. You also prove another couple of lemmas that says, if you have a planar end upstairs, whatever it maps to has to be planar. You can't create genus by going downstairs, but you can create it by going up. We saw that example of that hyperelliptic involution, right? That the genus vanished, but you can't create genus going down. So you prove that. If you're isolated and planar, this is something that's preserved under the covering. So you're isolated and planar downstairs if and only if you're isolated and planar upstairs. And as a result, you get that if you're isolated and non-planar and accumulated by genus downstairs, then you're isolated and accumulated by genus upstairs. These little lemmas you can prove, right? And it kind of tells you that, you know, upstairs, if you have genus and you don't have a bunch of punctures going towards it, you can't get rid of that genus. You can't do this trick. But the genus can't vanish unless it's accumulated by something. Then maybe you can make that genus vanish. Here are some curious consequences. These are, I think they were surprising to me when we came up with them, and they're still surprising to me. If you have a finite sheeted cover where upstairs you are a monster, the Loch Ness Monster, then downstairs you are the Loch Ness Monster. The only surface the monster covers is itself. The only surface the flute covers is itself. Right? Somehow these are sort of the minimal complexity elements in their commensurability classes. Really compelling question. Don't know the answer to. It's like, does this always happen? Does every commensurability class or if have a minimal element like this? And if not, which ones do? I think this is like these very basic questions. Very compelling. Same thing for the Cantor tree. You can prove that if you're a Cantor tree and you cover something else, got to be a Cantor tree. So what about some commensurability classes? Can we actually find some? Well, turns out we can. If you have finitely many ends, there are 2 commensurability classes. And you're infinite type. You either have a planar end or you don't. That's it. And your minimal element in those commensurability classes are these 2, a once punctured monster and a monster. If every end is accumulated by genus and you have countably many ends, you can pull some set theory from 100 years ago about countable closed subsets of the Cantor set and prove that there is exactly 1 commensurability class for every countable ordinal. And you might remember that there are, or maybe you haven't come across this, in which case that's great, but you might remember that there are uncountably many countable ordinals. So there are uncountably many commensurability classes. You can also prove that if your end space, forget about which ones are accumulated by genus, you just look at the end space. If the end space is a Cantor set, then you're commensurable to a Cantor tree. And in fact, you can show that every surface double covers this. Every surface with a Cantor set of ends double covers the Cantor tree. Let me give you a little example as to how this happens. Let's take the most extreme case, which is actually the easiest one to write down. I'm going to construct for you a 2-sheeted cover of the blooming Cantor of the Cantor tree by the blooming Cantor tree, which is unreasonable, again, to ask for. In fact, I spent a couple of weeks trying to prove it couldn't happen, and then I got a text from Alan one morning, He was like, I did it. You naysayer. Again, this is how our collaborations go usually. Just prove stuff that I try to disprove. Okay, so let's do it. We're going to build a cover out of building blocks. And each building block is very easy. Here's the building block. I'm going to take a genus 1 surface on the left here with 4 boundary components. And I'm going to arrange them like this. Okay, so one way you might want to think about this is you have your donut sitting in front of you and you skewered it, right, straight across. And everywhere you've intersected the surface of the donut, you sort of put in a little disc there. Delete a disc from around your thing, right? So that's what I've shown here. And now along that skewer, rotate by pi on 2. This is a perfectly good covering map. It's a hyperelliptic involution if there wasn't any boundary components. And what you're left with downstairs is a sphere with 4 boundary components. And each of the boundary components maps 2 to 1 down to its friend, whichever one is mapping to. So you get a degree 2 cover. This is great. Degree 2 covers everywhere is good because now I don't have to worry when I stitch things together. So what I'm going to do is I'm going to take a whole bunch of these covers and stitch them together. So let's take 4 more. So I start with this one at the bottom. And now I take 4 more. Exactly the same covering map. And what I'm doing is I'm keeping track of which boundaries map to which boundaries. Okay, that's what those colors are telling me. Because the map from red to red is 2 to 1, I can glue it over here and I will get a cover on my resulting surface. Or I can glue it here, and I'll get a cover of the resulting surface. Same with the blues, same with the orange, same with the greens. So I can glue them all down and I'll get a covering map from there to there. So now I have a 2-sheeted cover from there to there. And I was worried about this. So you do an Euler characteristic computation, and sure enough, everything checks out. It's all right. Doesn't seem like it should, but it does. Right? There's a 2-sheeted cover of a genus 5 surface, of a genus 0 surface with 12 boundary components by a genus 5 surface with 12 boundary components. Turns out, because it's there. Then you do it again, and then you just keep doing it. Right? And this is how you build the covers in general, this kind of idea, right? You take finite type pieces, you pay attention to what's happening on the boundary components, and as long as the degrees match up, you're home free. This is kind of neat. And then you get this like map from corals to corals. And everything's good. So you can play this game with a little more care for any surface which has a Cantor set of ends and show that it double covers a Cantor tree. So we have a commensurability class there. Cool. I'm going to leave you with that picture. Thank you for listening. That's a picture of Alan and I when we threw a party for all of Alan and his wife's friends right after we proved the theorem. Yeah.
Okay, why don't we thank Ty for a great talk? And we can